That's I can try to raise this a little bit.
We could move this forward if you want.
Yeah, I think that would
Square
work.
it up.
I like it when you wonder about the guy while they're talking.
Yeah.
Good.
Like the like bump. Anybody need a beer?
I'll take a beer.
Beer? Any preferences? Beer, Megan? You need a beer?
I'll take a cider. Whatever the cider is.
Okay. Best we decided. Okay.
I'll wait until you get back. Where is the one that we usually have? When was the last time you saw it? Are we good to get started? Hello, everyone. Hi. Good evening. How's it going? How many of you guys are attending AAS this week? Okay, come on. Awesome. Okay, cool. That's cool. So it's almost like half and half. For those of you who don't know, there is a rather large annual astronomy conference here in Seattle this week. called AAS, which stands for the American Astronomical Society. And so this is an extra special Astro on Tap where we have 3 speakers who are all PhD students here from other institutions attending the conference, and also, of course, here tonight to give their talks, which is great. Yeah. So tonight we're going to begin with Maggie Thompson, and she's going to be talking about strange new worlds, rocky exoplanets, and their atmospheres. Then Jack Lubin is going to be talking about the lives and deaths of Bernard B. And finally, you guys didn't show that love for Maggie. And finally, we're going to have Ryan Gallant? Okay, Ryan Gallant talking about the universe's magnetic mystery. Yes. So before we do any of that, I'm going to keep them away from you for a little longer, and we're going to do trivia. And now tonight is an extra special trivia as well because we have prizes sponsored by Startorialist. So the first place prize tonight is going to get a cool mug that has one of NASA's Mars travel posters on it, in addition to some postcards that have NASA travel posters on them. So it's a really good prize. Make sure you win, and you'll get it. Yeah, give me the prize. So how this is going to work, Tyler is here showing the first place prize.
There's a mug in the box. It's not just the box.
It's not just the box. So how? I said the postcards.
Okay.
So how this is going to work is we're going to go through the trivia. I'm going to put each trivia slide up for 30 seconds while you write down your answer. I'm then going to go back through all of the trivia questions, but only leave them up for 15 seconds. And then at the end of that, we're going to collect your trivia cards. And then Maggie's going to give her talk. In between her talk and the next talk, we'll announce the winners. And then once all of the talks are over, if you win, you can come collect your prize. Okay? Did everybody follow that? Okay. 1 minute. Thanks. Okay, so without further ado, here's the first round of trivia. Also, yeah. I actually know this one because I know the ones it's not.
You're just trying to like model her behavior.
You didn't cheat, did you? You didn't ask Megan.
Okay, I'm going to go back through each slide for 15 seconds now. This is your last chance to get your answers down.
Never gotten more than 6 out of 10. I mean, this is the love of the game, kind of. Not good, huh? The first one, really? You got a 6? My grade on the curve. They're wearing.
Okay, I hope you got your trivia answers down. Who thinks they won? Wow, you guys aren't very confident. Okay. Okay, so everybody, if you could now return your trivia sheets to Sam along with the golf pencil while we swap over to our first speaker, and then we'll get going with our first talk. Thank you. Every time. I know. I have a lot in my backpack. I'm gonna walk around tomorrow and
Okay, I think we have all the trivia sheets in. So, it is my absolute pleasure to introduce our first speaker. Up first is Maggie Thompson. We might as well call her Dr. Thompson, though, because she is in the last year of her PhD at UC Santa Cruz. She is originally from the DC area, and she has a dog named Rocket. So, it is my pleasure now to introduce Maggie Thompson.
Awesome. I'm gonna wait until I'm mic'd on both ends, so I'll use this for a little bit though. This is working okay.
Do both.
Cool. Okay, awesome.
Do both the whole time.
Okay. All right, I think I'm good. Hi everyone. I'm super excited. Thank you. I'm so excited to be here today. This is a really amazing crowd. You guys have our UCSC Astro on Tap beat at the moment, I must say. And I'm really excited to talk to you guys about exoplanets. These are planets that orbit stars other than our sun, and in particular, rocky exoplanets and the search for life in the universe. So before we begin, of course, I do not do all of this work alone. I have many awesome collaborators that help make this work possible. And so here, Miriam Tellis is my amazing PhD advisor, and I love her and aspire to be her. And Jonathan Fortney, these are people at Santa Cruz. But there's also some local people for you all. So both Joshua Chrysanthemum Totten and Nick Wogan, who's in the audience tonight, are both local to you all here in Seattle. They're both at UW. And they are awesome, and highly recommend that you find Nick tonight or Josh later and talk with them because they're amazing. Okay, so to set the scene here, we now know of over 5,000 exoplanets, planets that orbit stars other than our sun in the universe. This is huge, and to maybe date myself and all of you in the audience, we first discovered the first exoplanet around a sun-like star in 1995, and I was 1 year old at that time. You can date myself then. And one of the really cool things that we found when looking at all of these exoplanets is that both planets in our solar system and the planets that we found all around in the galaxy can be broadly divided into 4 different categories. And I've tried here to sort of give them beer flavors, but I am not a beer connoisseur, so listen to this and then tell me if you think I'm right. First, we have gas giant exoplanets. So these are things like your Jupiter, Saturn in our solar system. We also know of things called hot Jupiters. So we don't have one of these in our solar system, but they're these crazy bodies that are similar in size to Jupiter, and they are located super close to their host star, so they're crazy hot. So I was thinking these are kind of, I don't know, they're fairly common. They're like your lager. And so then another type, which are actually the most common type of planet in our galaxy that we know of, are Neptune-like worlds. So these are planets that are similar to Neptune. They are pretty cloudy. They have big hydrogen-dominated atmospheres. And these are kind of like a hazy IPA. And then you have your super Earths. These are pretty cool. We also don't have anything like this in our solar system. They are basically in between the size of Earth and Neptune. We think they're probably rocky and have atmospheres sort of like ours, so relatively thin atmospheres. And I'm going to call these a porter. I couldn't really come up with the best one, but I'll tell you why. It's because they're kind of related to the ones over here, terrestrial rocky worlds, which is what I'm going to be focusing on. These are very near and dear to my heart. We only know of out of all the 5,000 we found, only 4% are these rocky worlds. And we're going to learn about many more in the future. But still, no, 4% of 5,000 is still 200. That's a lot of these rocky planets. And these are the ones that we're excited to think about in terms of the search for life, because these are planets that are very similar to Earth. And they are really cute, and they're kind of like a stout because you don't want to drink too much of them, and they're dense. Okay, so just to put all of this into context in terms of the planet that we're standing on here today, there's one in particular, an exciting exoplanet system that has a lot of rocky exoplanets in it, and this is called the TRAPPIST-1 system. So this system is really cool. It was part of one of your trivia questions, so I hope you guys got it right. But this system has 7 known rocky planets orbiting around this star. TRAPPIST-1 is about 40 light years away, so it's going to take a while for us to build a spaceship and be able to actually get there one day. But this system is really cool because these planets are one of our best chances of starting to look for life in the universe because they're rocky. Some of them are also located in what we call the habitable zone. So this is the region where you're far enough away from your host star that you're not too hot, but you're not too far that you're too cold. We tend to call it the habitable zone or the Goldilocks zone. And just so you can kind of understand how this compares to our own planets in our solar system, here are the 4 rocky planets in our solar system: Mercury, Venus, Earth, and Mars. And you can see these are relatively similar in size. But this system is actually very different from our own solar system, and that's mainly because this TRAPPIST-1 system is crazy compact. You could fit the entire TRAPPIST-1 system within the orbit of Mercury. So this system, the star is very faint, so for the planets to potentially be habitable, they're located much closer in so that their temperatures are nice and warm. And so that's one of the things that we're excited to learn more about with these upcoming telescopes like NASA's JWST. So you might be wondering, okay, these are really cool, you know, of all these planets, but how do you actually study them? And so our main tool for doing this is a technique called spectroscopy. And this is a process in which we look at light that travels from the host star through the atmosphere of the planet. And you can think of this sort of like thinking about a rainbow. If there's certain gas molecules in this planet, as in the atmosphere, as the light's passing through, certain parts of that spectrum will get clouded, and then we'll be able to detect them using this spectroscopy method. And it's a really powerful technique to actually learn about these planets. And so the main window that we have for studying these worlds is their atmospheres. So the thin layer of gas, the air that we're breathing today, that we're all very thankful for, is the main way that we're going to be able to probe these worlds and actually study what their surfaces might be like, what their interiors might be like. So here, just to demonstrate this, I'm showing you, here on the left is Titan. This is one of Saturn's moons. It's actually it's the only moon in our solar system that has a significant atmosphere. And then all the way on the right, you see our planet Earth. And so we know certain things about both this moon and Earth's atmosphere, and that tells us a lot about the surface conditions. So for example, Titan is rich in nitrogen and methane. Based off of these atmospheric observations, we know there's these lakes of methane that exist on Titan's surface. And the Dragonfly mission, which you may have heard about, is going to be the very first time that we've ever sent a drone to another planetary body and flown it through the atmosphere of this moon. It's going to be crazy cool. And this exoplanet here in the middle is GJ 1132b. We're just starting to try to probe this planet and try to understand it. We think we've detected hydrogen, but there's a lot more we need to learn. And maybe this could tell us something about what the surface is like. Is it a lava surface? Is it rich in something else? And so the main thing here is that atmospheres are the main observational feature that we can study about these exoplanets. And so when you're thinking about, oh, astronomers, they've observed some other exoplanet, think about their atmospheres. Okay, so I wanted now to just talk a little bit about some of the work that I do in my own research. So I'm going to talk about two projects. The first is something that I do in the lab. I cook meteorites in the lab, and I get paid to do it, which is kind of crazy. And meteorites can actually tell us a lot about the early atmospheres of rocky planets. And then I'm going to talk about another project that I've had the real honor of getting to work with Nick on this, so you can talk to him more as well later, and thinking about if we want to see a planet that has life in it, what do we need to look for? And how do we be really sure that we are properly interpreting it and not just calling alien when it's maybe not there? So let's start with this first part. So we have to first ask ourselves, how do planets form an atmosphere in the first place? So there's two main ways that a planet can form an atmosphere. The first type are primary atmospheres, and these form by a planet just basically grabbing on to existing hydrogen-rich gas that's just floating around at the time that the planets are forming. And then the second type are appropriately named secondary atmospheres, and these form instead through processes like volcano eruptions, basically outgassing, or you can think of it as it's planetary farts, essentially. And while rocky planets might be forming their atmospheres through a combination of these two mechanisms, it's actually a very active area of research in the field of exoplanet science. Many of them are going to lose those primary atmospheres, and the main mechanism by which they are going to form any lasting atmosphere is through outgassing. So that's what I'm going to focus on. And so many of us that have been here at this American Astronomical Society meeting this week have been excited to learn about the fact that we're on this exciting new phase in exoplanet science. Now we're not just detecting exoplanets and counting them up, which is still really important, and we're still doing that, but we now can start actually characterizing what these planets are like. And in particular, what's the chemistry and what's the physics in their atmospheres. But unfortunately, especially for rocky planets, one thing that we don't have a good handle on is how do you connect the rock of your planet, the bulk or interior composition, to what its atmosphere is made of. And so in order to be prepared to do this and to interpret data that's coming up from the JWST Space Telescope and other ones that are coming online, we need to have a good theoretical understanding. We need the people that sit with their computers and run models to have a good understanding of what we think these atmospheres might be like. So what I'm showing you here are some very commonly used assumptions for what some rocky exoplanets' atmospheres might be like. We could be very wrong, but this is what we're starting with. And so on the left here, I'm showing you basically the sun. So this might sound kind of crazy, but this is something people do all the time. We just say, yeah, this planet has the same composition as the sun, or something like that. And then sometimes you can be really lazy and say, I'm just going to give this planet carbon dioxide, and that's it, and has nothing else. But that's okay. It's a place to start. And then lastly, this builds on complexity. You can assume that a planet is very similar to Earth. Give it Earth's composition, or give it Mars's atmospheric composition. But whatever you assume in these models is super important because it influences what conclusions you end up drawing about the planet you're observing. And so, okay, I'd now like to motivate how studying meteorites, these space rocks that fall to Earth, can be important for helping us understand what the early atmospheres of rocky planets might be made of. So to start, planets in our solar system are formed out of material that's similar to meteorites. You can think of meteorites as the leftover, like falling Lego building blocks of planets. And it's crazy cool that we are lucky enough that they just fall to Earth and are available for us to study. And what I just talked about at the beginning, rocky planets form their atmospheres through this outgassing or planetary fart process. And so if you measure what a meteorite outgasses, that can help inform what the early compositions are of rocky planets. Oh, sorry. So that's what I've been doing in the lab. I heat meteorites in a glorified oven, and I measure the things that they fart. That is essentially my entire, very large part of my PhD thesis. So this system here is a furnace that is connected to an instrument that's called a mass spectrometer. And this allows us to detect things like water, carbon dioxide, CO, and all of the major gas species that we expect to come off of these samples. So this, I always find these are sort of helpful, but not really. This is what it actually looks like in the lab. So this is my furnace in the kind of giant white gray box. And then that silver tube is connected to the mass spectrometer, which is that tiny gray box over here in the corner, this one. And so in the work that I've done, I've been looking at various meteorite samples. I've listed some of them here. And I wanted to share one funny story about one of these meteorites. So this one, Aguas Zarcas, is a meteorite that fell in 2019 in Costa Rica. And when it fell, parts of it fell through a doghouse, and the dog was named Rocky. So it was a rough wake-up call, but the dog was fine, thank goodness. There they are. It was all good. And basically several days after this fell, my advisor Miriam was contacted, and they said, hey, this meteorite fell in Costa Rica. Do you want some? And that is like my ultimate life goal, is for somebody to do that with me and ask me if I want a meteorite. So just so you know, if you ever find one, please give me a call. Okay, so the main things we found from this work is that when you're outgassing, these particular types of meteorites I looked at, which are really rich in these light, volatile elements, what we found is that you actually are outgassing a ton of water. And there's a lot of things like CO2 and carbon species. And all of this we know are important potential precursors and the ingredients that you need for life to eventually form. We're far ways off. This is thinking about the much earlier stage, but it's been a really exciting and fun project. And hopefully this can help us take a good step forward to connect what the rocky interior composition of a planet is and how that relates to its atmosphere. And then in my final few minutes, I'll just touch on a project about thinking about methane gas and how that's important in thinking about the search for life. And so to set the scene here with JWST, this is a very exciting time in rocky exoplanet science. We're at the very beginning phases of starting to probe potential biosignatures, signs of life in a planet's atmosphere using actual telescopes. And so there's been several proposed biosignature gases, and I just have little schematics of them over there on the right. It's by no means an exhaustive list, but many of these, maybe these are some you've heard of or seen in news headlines. You know, oxygen is a really great biosignature. Phosphine got all this headline because of Venus, and that kind of, we can talk about that later. Many of these are going to be actually really hard to detect with JWST. It's just we're not observing the particular wavelength features that we would need to actually be able to detect them. But methane is special because if it has Earth-like biological production rates, it's one of the only biosignatures that we actually could be able to detect with JWST. So it's really important we understand what you need to potentially see along with methane and what other signs you need to actually say, yeah, we think this is a biosignature. And so the reason that methane is a great biosignature gas is because it has a short photochemical lifetime. And what I mean by that is that when methane is in a planet's atmosphere, it interacts with light particles or photons, and then that breaks up your methane molecule, and then the hydrogen ends up escaping to space, and then you can't recreate your methane. So it doesn't last for very long. It lasts for like 1 million years or less. So that means you're going to need a lot of surface fluxes or sources that can produce a ton of methane to help counteract the fact that light is destroying it. And so one of the things we did together with Nick in this paper is we thought about, okay, yeah, methane on life today, methane is produced mostly by life today. You have cows farting. It was even more prominent way in the past. But there's also potential abiotic or just geological sources of methane. And so we wanted to investigate those in this paper, and this nice graphic here is showing you all the different ways you can make methane just through geology alone. So volcanoes, and Nick has an amazing paper that has looked at this in depth. You can have reactions like deep in the ocean between rocks and water that can generate some methane. And you can also have the big scary cometary impacts. Those thankfully aren't relevant to us today, but they were very relevant in the past. And we ultimately found that probably out of all of these, impacts is going to be your toughest bet in terms of something that's going to produce a lot of methane and maybe thinks you have a biosignature when you maybe don't, but the other ones aren't as concerning. And one of the last things we did to synthesize all of this work, hi Simcoe. Simcoe's telling me to get off. But what we did is we wanted to identify a procedure to tell us something about how can you identify a methane biosignature? You have an exoplanet, you've observed it, what is the order of operations that you need to go through in order to say, okay, yeah, I think we've actually got something super interesting here. Oh, I'm chosen. So the first thing is you want to really characterize your planet super well. You want to know what atmosphere composition is like. Does it have water potentially on the surface? Then you have to go through and rule out all these false positives or geologic sources that I just showed you. And very likely you're going to have to look for other things, even potentially surface pigments. That would be a crazy cool thing that we could learn about. So I'll just summarize that second project is we found that for rocky planets to have a lot of methane in their atmospheres, you need a source that's going to replenish that methane. And at least for Earth, the only thing that we know can do that super well is life. And we identified the different major important factors that would suggest that methane is actually produced by life and not just geologic sources. And so I'll just leave you with some final thoughts. I can't express this enough, but this is truly the most exciting time to be in the field of exoplanet science because we're actually starting to understand the wide diversity of rocky worlds and whether some of them could be habitable. Atmospheres are really important, and I think about this a decent amount of time when you see a pretty sunset or something. These are truly our main windows to studying these planets and searching for life. And lastly, I think it's very important that we use what we know about the things in our solar system, our planets and meteorites, to help us understand what these rocky worlds elsewhere may be like. So thank you so much. I'm happy to take questions. Yes?
What sort of temperatures you use in your furnace?
So we can go up to, we have actually two I've been working with. We can go up to 1200 Celsius. So that's like, oh man, it's hot. It's like, like 1,000, it's over 1,000 Kelvin. I have to remember how to do the Fahrenheit conversion, but it's hot. And when I go in, actually, often these take hours to run. So when I go in at night to check on them, the whole thing is just glowing red. It's pretty cool.
Did JWST today acknowledge its first exoplanet?
Yeah, no, they've already started observing multiple exoplanets. We've started especially with those more hot Jupiter worlds, the bigger ones, and the data looks so beautiful. It's amazing. Rocky worlds, we're getting there. Yes, and then orange in the back. I don't know. No, there's not. No, okay. Jack says no. I trust Jack. Orange?
Is the abundance of rocky worlds a detection thing, or do you think that might be actual abundance?
I think it's a detection bias thing. Yeah, there was a really awesome talk this week trying to give an estimate on how many Earth-like worlds there are. And right now we're saying it could be 5 to 100% of all stars have rocky worlds. So that's astronomers for you. I would like to say 50. 50 would be amazing. Yeah. Okay. One more. Yeah.
What are the abiotic sources of methane in space?
Oh yeah, great question. It's actually still a mystery. I actually think it's related to meteorites can help us with that. So Titan is farther out. It's orbiting Saturn. So it probably formed from a lot more volatile, organic, rich material that's unlike what the rocky planets like Earth formed out of. So you actually probably have a lot of that carbon and hydrogen just built into the building blocks. But it's a big open question for people. I don't think it's life. I think there's a lot of other ways you could make it, but it has been proposed.
Can you switch the slides over? Okay, let's thank Maggie one more time. Thank you. Can I have the slide advancer, please? Okay, before we bring on our next speaker, we're going to announce the trivia winners and the trivia answers. So the trivia answers, I'm just going to jump right into it. Number one, in 1992, astronomers found the first exoplanet around a pulsar. I can't pronounce that, Sam. Letter D is the detection method that has not been used to detect an exoplanet. Approximately 5,000 exoplanets have been discovered to date, as Maggie said, more than 5,000 actually. TRAPPIST-1 is located in Aquarius. Proxima Centauri b is the closest exoplanet to Earth, around an M star, similar to TRAPPIST-1. Charged electric particles cause magnetism. If a substance is naturally highly susceptible to being or staying magnetized, it is ferromagnetic. We discovered that the sun is magnetic in 1908. I don't know why I said we. It is true that the Earth's magnetosphere and atmosphere form a protective shield against the solar wind. It's also what creates our aurorae. And finally, all of the above is the answer for if Earth's magnetic field disappeared, this is what would happen. Okay, so I have 4 winners of trivia. They all got the same amount of answers correct, which was 9. Yeah. And since I have a 4-way tie for first, we're going to do a random drawing for who gets the mug, the best prize. And the other 3 people will also get prizes, but they won't be the mug and the postcards. Okay, so to start, I'll count them right now. There's only 10 questions. I'm just kidding. Okay, so to start, our 4 winners are Keebler Elves. Yeah. Okay. Interpolation situation. I like the rhyme. Bush League. And Rebecca. Okay, so now I'm going to invite up Maggie once again to select who gets the mug and postcards.
This is yours, David.
Thank you. Okay, so the ultimate winner of trivia is Interpolation Situation. Nice. Okay, so they and the other 3 trivia winners can collect their prizes at the end of all of our talks. And so, yeah, just wait for the end. Okay, so now I'm going to switch over the slides and get our next speaker ready to go. Give me 1 minute. Oh, it is. It just goes to the live stream, not the overall thing. That's why we use both. Yeah. You switched it?
Yeah.
Is this,
Is this it?
Yeah, this is it. Okay. I'm going to introduce him, but I need to consult my script first. Okay. Okay, 5th PhD, UC Irvine, East Coast, wants to work for the Yankees. Okay. Okay. Oh, okay, so at this time, it is my... Okay, at this time, it is my absolute pleasure to introduce our second speaker of the night, Jack Lubin. Jack is a 5th-year PhD student at UC Irvine. Yes? He is originally from the East Coast, and he says that if astronomy doesn't work out, he wants to work for the Yankees. So let's all hope astronomy works out. Okay, Jack.
So yeah, I'm Jack. I'm a 5th-year grad student, tentatively on the job market. We'll see what happens. And I'm excited to talk to you today about a very special planet that never was.
Take it out?
You can take it out if you want, yeah.
How's that? All right. So I'm a 5th-year grad student at UC Irvine, and I'm going to talk to you today about a very special planet that never was. So the multiple lives and deaths of Barnard B. So just a brief history of exoplanets. First, in the 1500s, Giordano Bruno imagined that every star in the night sky might host a planetary system like our own. And it was a wonderful idea, but it was heretical, so he was burned at the stake. Then not a lot happened until the 1970s when a guy named Peter Van de Kamp, as we're going to hear more about, he suggested there might be planets around Barnard stars. We're going to find out that was not the case. And then not much else happened until 1995 when Michel Mayor and Didier Queloz discovered the first planet around a sun-like star and kicked off the exoplanet era, if you will. And just like Maggie, I was also born in '94, so I was 1 year old. And it really just speaks to how young our field is and how far we've come in 28 years. So now we're going to get more into the talk. I'm talking about Barnard's star. We should probably talk about Barnard first, who he was. He was originally from Nashville, Tennessee. He was born into a very poor family. His father died before he was born, actually. And as all young people might have done in that age in a very poor family, he took a job at age 9 working in a photography studio. Photography was brand new at the time. And he was an assistant in this photography studio, mostly prepping the camera and so forth. So this sparked a very early interest in photography, which then led an interest into astronomy. Personally, I found that the Venn diagram of people interested in astronomy and people interested in photography is almost a circle for some reason. I can't explain it, but it is true. But later in life, after he established a family and so forth, he started feeling this astronomy itch again. And so he spent $380 in 1880, which was 2/3 of his income, his yearly income, to buy a telescope. And he saw this as an investment because there was a local wealthy benefactor who was paying people $200 for every comet they discovered. So he thought, I'll buy a telescope, find a few comets, it'll pay for itself, might make a little money on the side. And that's exactly what he did. He found 5 comets in a year, cool $1,000. He put down a down payment on a house and was later quoted as saying he built his house entirely from comets. So a very wise investment. As he started finding these comets, which were all the rage in the 1800s, the local Vanderbilt University decided that, hey, we should try to get this guy into our school. They were a young school at the time, founded in 1873. And so he accepted. He started a fellowship at Vanderbilt where he worked at the local observatory and took a few classes, but he actually did not graduate. He ended up dropping out, which is too bad. But this is the first point at which Barnard's life and my own have intertwined because I went to Vanderbilt and I did graduate, as evidenced by this picture. And what's even more interesting is that the building behind me in this picture is Barnard Hall, named after him. Even though he didn't graduate, he got a dorm. Everybody hated this dorm. It was awful. It was terrible. It was moldy. If you were assigned to this place, you had a bad year, basically. So, too bad. They've knocked it down since. Anyway, fast forward a little bit. He took a job at the brand new Lick Observatory in California. It's just outside San Jose. If you ever get a chance to go, you should absolutely go. They have a really great outreach program. They still do very active science. I was observing there on Saturday night remotely from here in Seattle. We didn't see anything. It was too cloudy. And anyway, he took a job there as an assistant astronomer. This is him posing with the Great Refractor at Lick Observatory. And here I am posing with the Great Refractor at Lick Observatory. But so he applied his photography skill to the sky and started taking images of the sky on photographic plates. And he was an extremely successful astronomer doing this. He did this for 20 years, and he actually later moved on to Yerkes Observatory in Wisconsin, but did this for a very long time. The most interesting thing that he did while he was there, in my opinion, is he discovered the 5th moon of Jupiter. So up to this time, there had been 4 moons of Jupiter that were known. They were called the Galilean moons because they were discovered by Galileo in the 1600s, early 1600s. And it took almost 300 years to find another moon of Jupiter, and it was done by Barnard. He did it looking through this telescope, and this is his notebook from the night he made the discovery. The support astronomer at the mountain showed me this while I was there. He was also an excellent artist, as you can see. But what's really interesting is I'm going to zoom in on this region. Here's Jupiter that he drew, and then he puts a dot and he writes object, very descriptively. And he writes in his cursive, this is some kind of satellite or elongation. I don't know what an elongation is, but it was a satellite of Jupiter. And so what's so cool about this is that this is the last time, 1892, it's the last time that somebody looked through a telescope and discovered a body, a planet, or in this case, a moon. Every planet that's been found since then was using photographic plates or supercomputers. So the end of an era, basically. But what he's maybe most famous for and why he got a star named after him was, well, he found what is now a famous star, Barnard's star. He was looking through his old photographic plates and he noticed that one star was a bit out of place, which how many people would notice that if you looked at the sky? But he did. And what he discovered is that this is actually the fastest, what's called proper motion star in the sky. Proper motion is the apparent movement of a star through the sky. And here's a little animation showing Barnard's star. You can see relative to the background stars, it is moving very fast. The other stars are essentially not moving. But all stars do this. It's just that most don't do it very quickly. And so this was a bit of an oddity at the time. And so he got to slap his name on it. What we now know is that Barnard's star is actually the second closest star to our own. It's right next door, basically. It's only 6 light years away. Got an arrow pointing to it. Unfortunately, it is too dim for your naked eye, which is why he needed photographic plates to discover it. But it's a very red and very old M-dwarf. It's probably one of the first stars in the galaxy. It's very, very old. And it is rocketing across the night sky at a rate that you could never discern with your naked eye. It's also very popular in science fiction. This is just an abbreviated list of sci-fi books and movies that have placed a fictitious planet in the system. It's usually used as like a refueling station on the way back to Earth. It's not usually a great place to visit. But it is included in science fiction quite frequently. And on that note, I'm going to take my talk a little bit towards the science fiction, if you will, and I'm going to frame everything in a Star Wars sense. I hope it makes sense. You'll judge me on the end, I guess. So a long time ago, galaxy far, far away, we start with the Phantom Menace. The first life of Barnard B, it was a phantom. It was first discovered by this guy, Peter Van de Kamp, as I first kind of teased a minute ago. He was working at Swarthmore College, which is in Pennsylvania, using this telescope here on the right. And he was using a method that we call astrometry. Astrometry is measuring the apparent circular motion of a star in the night sky. So imagine this is in the plane of the sky. It's not edge-on, it's a face-on system. And you can't actually see the planet through your telescope, but you can see the star. And if you can observe the star tracing out this very small circular motion over some amount of days or years, then you can infer that it's the planet gravitationally pulling on that star, creating that motion, and then you can infer the planetary mass in the planetary period. So this is what Peter Van de Kamp was looking for as he was observing Barnard's star. And it requires these really precise photographs and measurements of where the star is in relation to every other star around it, which, as I've already said, is very difficult for Barnard's star because it's rocketing across the night sky. But here's a maybe example data set. This is not a data set of Barnard's star, it's just some random star. You can see that as the star moves it through its proper motion, which is the dashed line, it's a very smooth, straight line. But an unseen planet will cause these deviations in the path of the star. And so he measured in 2014, 2015, 2016. You can see it moves from one side, the bottom side of the dashed line, to the top side of the dashed line. This is an indication that there's something gravitationally interacting with the star, and it's most likely a planet. So this is what Van de Kamp was looking for. And he said, I found the first 2 planets. He had about 30 years of data on Barnard's star and was able to claim, and I use that in air quotes, 2 planets, both about half the mass of Jupiter and on dozen to 20-year orbits. And he was really proud of this. He wrote 2 papers about these planets. He later wrote more, as we're about to see. but he was adamant that he found the first exoplanets in 1968. Unfortunately, we're entering phase 2, Attack of the Clones. In this case, the clones are these two guys, George Gatewood and Heinrich Eichhorn. They collected an equally large data set on Barnard Star using 2 different observatories, and they reported no astrometric detection of a planet. So now you have one person who says yes planet, 2 people that say no planets. Who are you going to believe? Well, it's time for a third voice, the Revenge of the Sith. And in this case, the Sith is this guy, John Hershey, who reanalyzed the exact same photographic plates that Peter Van de Kamp used, and he determined that the astrometric signal that Van de Kamp claimed was due to planets was in fact due to every time they cleaned the telescope, it introduced an offset in the data that Van de Kamp had not accounted for, and therefore completely explained the proposed planet. So this guy is responsible for the first death of Barnard B. That's Life 1 and Life 2. Life 1 and Death 1. So that takes us into the original trilogy. We have A New Hope. In 2018, a new team, mostly based out of Europe, international organization, they claim a new planet in the Barnard Star System, totally different than the one that Van de Kamp first claimed. They say it's a super Earth. It's about 3 times the mass of Earth. It's on a 233-day orbit, so about 2/3 of a year. And they say it's there. How did they do it? They used a different method from astrometry. It's called the radial velocity technique, or the RV method. The RV method, I'm going to explain it, but we're going to start from a stellar spectrum. Maggie hinted at spectroscopy earlier. We're going to do a little more of that now. So this is what we might call an ideal spectrum. A spectrum is just a measurement of the intensity of light on the y-axis at different wavelengths of light on the x-axis. And this is, again, ideal in the sense that this doesn't exist in nature, but we might hope that it did. A real spectrum looks like this. It's got a lot of jagged edges. It's got a lot of these dips, these very, very deep, we call them absorption lines. And I'm going to explain what an absorption line is in a second. But by taking stellar spectra, we can infer planetary existence, essentially. I'll show you how we do that. So we have these absorption lines. What is an absorption line? Well, if we have a star, maybe like our sun, and a planet like our Earth, photons, the light sources of stars, are generated inside the cores of stars. And then as they move out from the core into the atmosphere of the star, eventually they leave the star and they hit us here on Earth, and that's how we see the star. However, not every photon ends up leaving the star. Some photons with very specific wavelengths leave the core of the star. They interact with atoms and molecules in the atmosphere of the star, which absorb them and then re-emit them in random directions. And so this photon never actually reaches Earth, and so we don't see it. And this is what's happening in spectra with these absorption lines. These are very specific wavelengths in which we don't see as much light as we would expect coming from the star, due to this absorption aspect of stellar atmospheres. And so just like this graph on the top, which has these jagged absorption features, we can plot them in a different way with this continuous rainbow on the top and these dark lines, which are indicating where the absorption features are. So if you imagine, if you keep this image of a rainbow with these black lines blotted out, keep that image in your mind. And now we're going to talk about the radial velocity method. We first talked about astrometry. Astrometry happens, you're looking for the motion in this plane of the sky. The radial velocity method, we're going to tilt that 90 degrees and look in this plane of the sky. So astrometry, we would say this is a face-on orientation of the system. In radial velocity, we're looking for an edge-on orientation of the system. And so an observer here on the left side views, they're both moving in circles, but from our perspective, we see it as only towards and away from us. And as the star moves towards and away from us, the absorption line features in the spectrum move due to the motion of the star. And if we can measure that changing absorption feature in the spectrum of the star, we can infer the motion of the star and therefore infer the existence of the planet. So we're playing like a couple levels of inception here. but like this. This is a very simplistic view of a stellar spectrum with a single absorption line. And what we're looking for is this very subtle back and forth shift of this absorption line over some kind of time scale, days, weeks, years, whatever it is. However long the planetary orbit is how long this back and forth shift will happen. So we're looking again for this translational shift in wavelength space. And now it's time to kill Barnard B again. Because the Empire is striking back, and in this case, I'm the Empire. So planets aren't the only thing that can induce these absorption line shifts in stellar spectra. Stellar activity, which are things like star spots on the surface of the star, they can trick us into thinking that the absorption lines have shifted, when in fact they really haven't. And what I mean by that is, imagine a spot on a star. As the spot rotates into view, the absorption line kind of wiggles. And if you're not careful, you might think that the wiggling is the same as the shifting. And this causes a lot of problems with finding exoplanets. Very often, well, not very often, but sometimes you might claim a planet shifting back and forth in that spectrum, when in fact it's just lines doing this kind of wiggle. And so that's what happened in Barnard's star. But even worse, when you get this stellar activity effect, you can get what's called aliasing. Aliasing is when you can no longer tell the true orbital period of the planet because multiple orbital periods fit the data equally well. You can't untangle. So what do I mean by that? Well, here's a data set that I cooked up. It looks like a signal that exists over a 30-day time span. You can draw a line through these data points. But you can also draw an equally good fit at like 2 days. And there's no way that you can tell the difference of which is the true period and which is not. And this is what happened with Barnard's star. We had a strong stellar activity effect, which caused an extreme case of aliasing, and it allowed me to write a paper about it. Stellar activity manifesting at a 1-year alias explains Barnard B as a false positive. So this is the second death of Barnard B. And the only reason I chose the Star Wars theme of this talk was so I can play this clip. Unfortunately, this was a byproduct of our work. We didn't set out to do this. The goal was not to kill a planet. The goal was to study stellar activity, and in the process, we made an unfortunate discovery. And I mean that wholeheartedly. Anyway, we have to finish out the 6th movie here, Return of the Jedi. In this case, the Jedi is going to be Barnard B, because our paper did not rule out planets in the system. We only ruled out this particular planet that was claimed, this 3 Earth mass super Earth planet on a 233-day world. We were very optimistic that there could be a planet in Barnard's star. In fact, it would be strange if there wasn't. We know that from statistics, most stars have at least one planet in the system. So why doesn't Barnard's star have a planet? We don't have an answer to that yet, but we're still looking. We have a worldwide network of telescopes. This is just a schematic of roughly where they exist in the world. These are the top instruments in the world, taking data every night that the sky is clear. Some of them are taking data of Barnard's star, some of them aren't. But we're hopeful that one day we can combine a huge superset of data and pull out a real planetary signal in Barnard's star system. So with that, I'll leave it to you. That's my website. You can follow me on Twitter if you want to hear more. And thank you very much. So now we'll take some questions. Yeah.
Is there a distribution of exoplanets based on the generation of star? Like first generation stars are less likely or more likely to have planets?
Yeah, that's interesting. So the question was, is there a distribution of planets based on stellar age? As far as I know, there's a strong correlation between the metallicity of the host star and the amount of planets in the system. So more metal-rich stars tend to have more planets. And similarly, more metal-rich stars tend to be younger. The older the star is, did I get that right, Brian? Yeah. The younger the star is, the more metals that it probably has. So young systems, which are always being born, tend to maybe have more planets than otherwise. But that's just kind of a correlation, maybe not a causation. Alex?
You met the people that claim they discovered Barnard?
He asked if I've met the people who couldn't discover harmony. I've met a couple of them. They're very, very nice. We have a professional relationship, and we disagree professionally. Yeah. Yeah.
So do you think this process of discovering a planet and having to dig, disprove it, and discovering it again, is that something that's unique to Barnard B? Or do you think as we dig into all these detections from TESS, from JWST, et cetera, are we going to find out that a lot of these planet detections are maybe due to the phenomena you talked about today?
Yeah. So the question is this process of life, death with Barnard B, is this something that we might expect to happen repeatedly with other stars? I tend to think no. And the reason for that being is that the first life and death of Barnard was kind of a fluke. It probably never should have happened. And today we also take very strong steps to ensure that our targets are real. This case was a very particularly insidious case of stellar activity. The team that claimed the planet did absolutely nothing wrong. We just did a really, really deep dive, deeper than maybe anyone should, and we came up to this conclusion. But so in the future, I think that there will still be death planets, but it'll be more rare and it'll be more in specific cases. Okay. That might be it. Oh, yeah. So the question is, how do we like filter out the sunspot activity so that this doesn't happen again? And if you could solve it, they'll give you a PhD at a Nobel Prize. So we're working on it. That's actually a huge part of my thesis that is still not fully solved. Yeah, thank you.
Nice. Okay, two fantastic talks. So very shortly, we're going to invite up our third and final speaker of the evening. But before we do that, we're going to take about a 5 to 10 minute intermission break and do last call here at Bickerson's. So if you want to get one more drink, now's the time to do it. And we'll reconvene in 5 to 10 minutes. Somebody so many. Yeah, I was going to announce it at the end of the last talk, too.
pivoting, right? Yeah, so they started out as like a hardware company, like lighting, so you all the way out of software.
Yeah, that's a big sometimes I question. So I was working with like data science and software related stuff mostly, but yeah, I think it was like always trying to go back to yeah, I just wanted to like work in a different for a while since like the work I do now is really in data and stuff.
Yeah, like software, like pipeline development. Oh yeah, how do you like living here? I'm sorry. I really wish I could move to Chicago. I think maybe I would like. Yeah, my last time I went, either out, yeah, out for sure. For us, are you? Yeah, I would like to. Yeah, I'd like to go for it. I only applied like five places. So my partner is a medical student and like studying both on Long Island and right now. So I basically only applied to like East Coast places. I applied to Caltech, but I don't know why I did it. I just like applied, but I didn't like feeling like the ever like so I honestly have no idea why I didn't do it. But yeah, that was like the only other place I applied. That's interesting. I didn't realize that there was such an opportunity.
And I know it is constant.
Yeah, I should
Because I know what you're drawing.
Yeah, I don't know why I applied. I don't know if you should get into that's awesome.
It's just bad.
Yeah, I think that's all about it. Yep. 15 minutes. Good luck. Hopefully somebody saw it and like will give me a and how long are you expecting? Like a Friday or
I'm like,
That's funny. Only Tom. That's very Tom specific.
I mean, it sounds like it is, right?
yeah, it's just not that it keeps getting pushed back. Like I was at the movie town yesterday and it just got pushed back a couple of times.
Although did you
So when it's still a big deal, like, you know, like, hurry and hurry.
that's just anything, right?
Yeah.
After you get
So you went through a PhD based on something that doesn't make sense.
So the funny thing is, like, I got in and then I took another gap year because I was like, oh, this is perfect. I'll like go where I'm going and then movie data will be available in like 2022. And then the pandemic happened and I like already right as well.
Yeah, I remember when I was visiting grad school, people were like, yeah, you should come here because we'll get like tons of JWST data. And I'm like, well, good thing I didn't do that because like I would be like at the end of my PhD and barely have done anything.
think we should get going. Okay, welcome back, everybody.
Hello. Did everybody do their last year? Yeah. How's it going? Hi. Thank you, Andrew. Everybody's excited for the last day of the conference tomorrow. Yeah. Yeah. Okay. Okay,
Okay,
so
so at this time, it is my
pleasure to introduce the third and final speaker
of the evening.
Is everybody ready for the third and final speaker? Yes. Okay, so at this time, I'd like to introduce Ryan Gallant. He is a third-year PhD student from Columbia. He's originally from DC, and in the words of Ryan Gallant, there are no fun facts about me. So, at this time, I'd like to introduce Ryan up to the microphone, please.
Okay. So, I'll be giving this talk as my detective alter ego, Benoit Plunk. And I did bring a fake mustache, but it lost its stick. But the first rule of being a detective is to bring an extra fake mustache, which also lost its stick. So, the second rule of being a detective is to grow your own mustache, and that did work. So, 1 second. So, let me set the scene. The year is 2023. I'm seated in my office, hunched over my computer, poring over paper after paper. But things just aren't adding up. One paper says one thing, another paper says another. Who do I trust? Who do I believe? It's a jungle out there, and the only person I can trust is myself. But I just had to know, what magnetized the universe? Well, I don't know much, but I can tell you this much. Whatever magnetized the universe has left behind plenty of fingerprints. And we've all seen these fingerprints. At some point or another, we've all felt that invisible push, the invisible tug of magnetic fields. So if we're going to track down what magnetized the universe, first, I'm going to need some help from all of you. Where in your everyday life have you guys seen magnetic fields? Have you felt magnetic fields? Magnets. Okay. Very good. Okay. Magnets. Anybody else? Induction cooktops. That's a great one. Very interesting. Yes. Okay. Credit card. All very good. Okay. All very good examples. I've taken notes. So, let me tell you one thing. Whatever magnetizes the universe has left magnetic fields everywhere. And this brings us to crime scene number 1. Our home, the Earth, has its own large-scale magnetic field. If you've ever used a compass and you've seen the little jiggling of the pointer, that's the direct effect of the Earth's magnetic fields. If you've seen an aurora, that's the direct effect of charged particles from the sun interacting with Earth's atmosphere. Now, our friends down in geophysics tell us that the Earth's magnetic field is amplified and sustained by a dynamo, that the sloshing and stirring of electrically conducting fluid in the Earth's outer core gives rise to a varying electrical current, and that current gives rise to a large-scale magnetic field. Very interesting. But we don't only see dynamos in the core of the Earth. We also see dynamos throughout the cosmos, which brings us to crime scene 2. Stars, like our sun, are filled to the brim with magnetic fields. Stars are completely comprised of plasma, of free-streaming electrons, ions, free charges, all whirling about in a really big, electrically conducting fluid. So, when we have these little charges all whirling about, all stirring about in the middle of a star, we get currents, and those varying currents give rise to a dynamo, and that dynamo gives rise to magnetic fields. Sunspots, solar flares, the solar winds, coronal mass ejections, all the activity that we see around stars and in stars is a direct result of magnetic fields. Now, as we start to zoom out a little further, things get a little more hazy. Crime scene 3. Galaxies are also filled with magnetic fields, as you can see from this mugshot of our Milky Way. But despite our best efforts to model a galactic dynamo, we just can't reproduce the magnetic field strengths that observations tell us should be there. We're always falling short. We're missing some ingredients, and we don't know what it is. Another interesting thing with galaxies is that for the vast majority of galaxies we've observed, the old ones, the new ones, the distant ones, the close ones, all of them have strikingly similar average magnetic field strengths. So this is pretty strange, pretty peculiar. But I'm going to show you something even peculiarer. Crime scene number 4. On the largest scales, the universe is organized into a vast cosmic web where galaxies and galaxy clusters are threaded together by long filaments of gas. But in between those filaments are cosmic voids, so named because they are incredibly underdense, the least dense regions in the universe. Now, while there may be a smattering of a few galaxies in each of these voids, the average density in a cosmic void can dip down to 27 orders of magnitude below the density of air at sea level. So that's 27 zeros after that decimal point. That's approximately equivalent to 1 proton per cubic meter. For the Americans in the audience, that's about 1 proton per 280 cubic hot dogs. But, so, if there's nothing in these voids, they're practically empty. How are we going to get currents? How are we going to get dynamos? How are we going to get magnetic fields? I mean, if there's nothing in there, we can't get magnetic fields, right? I'm firmly of the belief that there are no magnetic fields in voids. And raise your hand if you're with me. No magnetic fields in voids. Good. Yeah, so I'm gonna double down on that. No magnetic fields in voids. Damn it. Foiled again. There are magnetic fields in voids, and we have no idea why. So, okay, give me a second. So this is puzzling. If there are magnetic fields literally everywhere in the universe, then when did they come into being? When in cosmic time did these magnetic fields form? Well, if we want to pinpoint exactly when this crime occurred, we can refer to our handy-dandy universe timeline. Now, on the far left of this diagram, we have the beginning of the universe, the Big Bang. And 14 billion years later, we have the present day on the far right. So let's see. Some people think that these void magnetic fields first arose at the epoch of inflation, within the first 10 to the minus 32 seconds after the Big Bang, when the universe expanded in volume by 78 orders of magnitude. Okay? Some people think those magnetic fields first arose a little later, at the quantum chromodynamic phase transition, when the strong force, the force that binds atomic nuclei together, became its own independent thing, independent of the other fundamental forces. Seems reasonable. Others think that these magnetic fields arose a teeny bit later, at the electroweak phase transition, when electromagnetism became its own thing. So I'm starting to see a bit of a trend. All of these scenarios are happening very, very early in the universe, within the first microsecond of the universe. So, oh no. Yikes. Some people think that these magnetic fields that fill the voids arose maybe a little bit before or a little bit after the formation of the first stars and galaxies. And this is a bit of an issue. If I'm reading this correctly, okay, just what I thought. That's a 200 million year margin of error on the timing of magnetic galaxies. And admittedly, that's not a great look. A little disheartening. I mean, we have this much uncertainty on when the magnetic fields arose. How are we ever going to find what magnetizes the universe? So, I mean, should we just give up now? It's over. It's a lost cause. No. Never give up. Never surrender. Whatever magnetized the universe is holding a great deal of information, and we need to extract that information. So, what are they hiding? Well, as we know from observations of the nearby universe, magnetic fields play a key role in the formation of stars and in the structure and evolution of galaxies. So, if we want to figure out how the very first stars and the very first galaxies formed, we need to understand what the magnetic fields in the universe were like way back then. If we want to precisely figure out how fast our universe is expanding, maybe magnetic fields could help. Currently, we have two well-supported but disagreeing values for the expansion rate of the universe. And we can't figure out why there's this tension, why we can't reconcile these two values. But if we have sufficiently strong magnetic fields, sufficiently early in the universe, maybe that could resolve this tension. Another weird anomaly in our universe is that there's much, much more matter than there is antimatter. And we have little idea why there's this asymmetry. But again, magnetic fields in the early universe could be the solution, could explain this matter-antimatter asymmetry. And just in general, our knowledge, our understanding of the very early universe, the first few seconds, the first few minutes, is hazy. But if we can trace back magnetic fields in the present day, all the way back to millions or billions of years ago, we have a direct window into the infant universe. So trying to figure out, or trying to catch, whatever magnetized the universe is absolutely a worthwhile effort. And luckily, we don't need to go about this alone. We do have some informants in the field, some people on the inside, if you will, that are very good at mapping the magnetic fields throughout the cosmos. So first we have our friend, Faraday rotation. When a wave of light passes through a magnetic field, it gets rotated or twisted ever so slightly. We can see this best in radio waves. So if we can find a radio source, and we observe that source from the Earth, and we measure how much that radio wave has been twisted, then we can infer the strength of the magnetic fields between that radio source and between us. Very cool. We also have our buddy, the blazars. These are very powerful black holes, sucking in a whole bunch of matter and expelling that matter as a powerful jet right in our direction. So if these jets of matter were pointed directly at us, we'd expect to see a small concentrated source, a little point of light. But when we look at these blazar jets through cosmic voids, we don't see a point of light, we see an extended halo or a ring of light, which suggests that maybe magnetic fields are afoot. And of course, we have our very, very old friends, the cosmic microwave background, or the CMB, the oldest light in the universe that we can see. And the data we have on the CMB is exquisite. It's some of the best data we have in all of astrophysics. So we can pore through that data, look through little blips or distortions in that CMB data, and maybe that can point us to magnetic fields. But unfortunately, as hard as these informants work, and as much data as we get from these informants, they alone can't tell the whole story of what magnetized the universe. We need to do a little bit of hacking into the mainframe to complete the picture of what magnetized the universe. So we need to couple the data that we get from those observational informants to data from computer simulations. So, for example, we can use cosmological magnetohydrodynamic simulations, which unfortunately does not fit on a Scrabble board, but if it did, it would be a pretty awesome word. I mean, that would be like hundreds of points. And it's a really big word, a good word. But okay, these cosmological MHD simulations simulate huge volumes of space over huge amounts of time. So we can plug in some initial conditions, and then we just let this simulation run, and we can see how this volume of the universe expands or how it behaves over long periods of cosmic time. The issue with these very large-scale cosmological simulations is that they can't resolve the small scales where magnetic fields are actually being generated. So for that, we need to use what are called plasma kinetic or particle and cell simulations, where we resolve the individual particles in the plasma, the electrons, the ions, all stirring about. And with these simulations, we can actually probe how the magnetic fields are being generated. So we can take the results from the plasma kinetic simulations, plug them into the initial conditions of these huge cosmological simulations, and then see how these magnetic fields have grown, evolved, how they behave across the timeline of the universe. Unfortunately, at the present day, even this is not enough. We still can't figure out what magnetized the universe. So what more do we need? What other evidence is there? On the observational front, we still need to observe light across the entire electromagnetic spectrum. We need to observe and collect gravitational waves. We need to study the super energetic particles called cosmic rays and the super, super, super energetic particles and very tiny particles called neutrinos. On the computational front, we need to build longer, better, faster simulations that we can push to high resolutions to approximate reality on the computer. And we need to understand our arch nemesis, turbulence. Of course, wearing the universal mustache of evil. And can I just get a quick boo for turbulence? Like, good. Okay. Yeah, that's very cathartic. Turbulence is a thorn in every physicist's side. Yet, we know that turbulence plays an important part in the behavior of plasmas, and thus plays an important role in the behavior of magnetic fields. So, until we can defeat our arch nemesis, turbulence, until we can supercharge our computer simulations, and until we can collect data from messengers at all corners of the universe's magnetic mystery remains unsolved. Thank you. All right. Thank you. Okay. A few questions. Yes.
Can you explain a little bit how neutrinos are connected to like magnetic fields being neutral?
Right. So I'm not an expert in this, but I do know that neutrinos carry their own energy density and chemical potential. So for the very early magnetogenesis scenarios, like the quantum chromodynamic transition, you need a specific chemical potential in the neutrinos in order to get that phase transition. So we need to better understand, the whole neutrino budget in the universe. And also the neutrinos contribute to that whole mass energy budget, which could alter how we're studying these early magnetic fields. Yeah.
Are there any connections between what we know about magnetic fields and what we know about dark matter?
So I don't think so. So dark matter, since dark matter doesn't interact with light, doesn't interact with the normal electromagnetic force, so there could be an entirely separate dark sector of electromagnetism, but I don't think we've done much work with that. Yeah.
With the antimatter versus regular matter, is there any association with how magnetic fields connect antimatter as opposed to matter to explain the difference in matter?
So I think the leading idea is that in the very early universe, there was some symmetry that was spontaneously broken. So we start out with some symmetry between the matter and antimatter that was broken, that led to much more production of matter than antimatter. And so some quantum electrodynamic effects involved in these magnetic fields could have caused that broken symmetry. But yeah, it's very, all right, one more question in the back. Sorry, wait, could you say that a bit louder? Yeah, so I'm not too sure about that. But I do know, yeah, so if the magnetic fields were generated primordially in the very early universe, they might have some influence on the cosmic strings and that type of stuff. And I do know with like the QCD and electroweak phase transitions, that leads to like bubble nucleation. So these bubbles in space that can give rise to magnetic fields. So, yeah. Yeah. Thank you.
Okay, you can just give me the. You just give it to me after.
Oh.
Okay, let's give one more round of applause to all of our fantastic speakers today. And I'd just like to personally thank them for traveling all this way just to give an Astro on Tap talk. And how convenient is it that the conference happened to be the same week, right? Okay, so before I let you go, I wanted to mention, or actually first I want to invite up Frank, who I think has something to say. Yeah, Frank.
I don't have any jokes or anything, but my wife and I are the owners of Bickerson's, and so we wanted to thank you all for coming out tonight. I hope you had a good time. We'll hopefully see you back next month.
Okay, and before we go, check out our social media as we'll announce the date for February Astro on Tap here at Bickerson's. But we are also going to be having a special edition Astro on Tap tomorrow next to the Convention Center at Optimism Brewing. That'll begin at 7 p.m. just like tonight, so we hope that you can make it out there as well. And look out for our February posting for Astro on Tap here on Bickerson's next month. Thank you. Oh, and don't forget to get the trivia prizes if you won. Yeah. Okay.
Where is my
Trivia prize for. Oh, you should get that.
yeah? Who's it? Whatever.
Hey, Sam, can I just unplug the frost?
Yeah, whatever you want.
That's public.
I should go to find her.
Okay, you got it.